So here I have a problem of how we might approach a two-dimensional kinematics problem. So I have a pumpkin that is being launched in a pumpkin launching demonstration with a speed of 80 feet per second at an angle of 30 degrees from the horizontal. So it's going to go take off in this direction. And if we've ever seen something get thrown like this, we know that it'll make some arc through the air and eventually hit the ground at some position. And I want to know how far away from the starting position does the pumpkin hit the ground. And I also know that this is being done on Earth, and so our acceleration is in the y direction, so assuming our y is our up and down direction, is negative 32.2 feet per second squared. So now to solve this problem, I am trying to find the position. So we used r for position vector. We want the as a function of time so that I can figure out what that is when it hits the ground. So the easiest way to do this is actually to break this up into x's and y's and look at them separately. So in the x direction, what I know is that I have an initial velocity. I'll call it v naught, so for v naught but sub x, comma x. That's going to be our 80 feet per second, but only the x component of it. So we're going to multiply this by the cosine of that angle, 30 degrees. And I calculated this out and I got an initial velocity of 69.3 feet per second. And then I also have a y direction. So in the y direction, I also have an initial velocity, so v naught sub y. And that's going to be my 80 feet per second. And now the y component of that, that's going to be the vertical component, is just going to be the sine of 30 degrees. And so this is 40 feet per second. And now we treat these totally separately. And I'm actually going to start by looking at the y direction. So I know that I have an initial velocity of 40 feet per second. I know that I have an acceleration in the y direction of negative 32.2 feet per second squared. I also know that my initial position in the y direction, I'm going to go ahead and call my origin exactly where it starts. So I put my directions here, my origin should really be right where it starts. So I'm going to say my initial position in the y direction is 0 feet. And the other thing that is really helpful in this problem is that the final position in the y direction is also 0 feet. So my final y position will also be 0 feet because it's going to come back and hit the ground. So using these things, if I go look at my kinematics equations, there's actually a really helpful kinematic equation that has initial velocity, acceleration, and position, and time. So if we can figure out the time, I think that will help us in the x direction. So that kinematics equation is that our SF is our 1/2 a t squared plus v naught t plus s naught. And I know everything in that equation except for time. So if I go ahead and plug that in, I have 0 is equal to 1/2 negative 32.2 feet per second squared times my unknown time squared plus my initial velocity in the y direction, so that was 40 feet per second times time plus 0. Hopefully we haven't totally lost that. And I can solve for time here now, so my time ends up being either 0, this is a quadratic, so there's two options, or the other option is 2.5 seconds. So those are the two times that this is actually at the y position of 0 feet. So it's at a time is equal to 0 and at a time 2.5 seconds that it hits the ground. So if I'm trying to figure out the final position, I'm going to go ahead and use that 2.5 second time. So I'm able to use the y direction here to help me solve this problem for the time, and now the x direction is with that time is how I'm going to figure out where it went. So my acceleration in the x direction here, this is an assumption that we normally make with these kind of projectile motion problems. where we have a large y acceleration, is we'll go ahead and assume that that is a 0. So this is an assumption. Usually there is some acceleration in the x direction by air resistance. You can imagine that pumpkin is going to push through a lot of air as it does this, but it's going to be pretty small, especially relative to the 32.2 feet per second squared. And just in 2.5 seconds, it's not going to slow down a ton. So this is a pretty reasonable assumption, although we can talk about later in this class, and especially you'll talk in fluids about how we might do a better job correcting for this. And also we know in our x direction, the initial position is 0, and we're trying to find our final position in the x. And that will happen at a t 2.5 seconds. So now going through my kinematics equations with an initial velocity, acceleration, and position information and time, actually that same kinematics equation is going to work really well to figure out the position, or yeah, the final position. So I'm going to use SF is equal to 1/2 a t squared plus v naught t plus s naught. And now plugging in, we're trying to solve for our SF. We have 0 acceleration, so I don't need to worry about that first term. My velocity is 69.3 feet per second. I'm going to go for 2.5 seconds, and my initial position is 0. So this gives me a final position of that pumpkin of 173.3 feet. So that pumpkin has traveled 173 feet in those 2.5 seconds, and that's where it collides with the ground. So one thing I want to warn you against here, these equations that I'm using, the SF is equal to 1/2 a t squared plus v naught t plus s naught, those assume constant acceleration, which is great the whole time the pumpkin is in the air, and it's great until the instant the pumpkin touches the ground. After the pumpkin touches the ground, there's going to be a massive change in acceleration as that pumpkin comes to a complete halt. It is tempting to see this equation, or more commonly to see the v squared is v naught squared plus 2a delta s, this equation, and say, hey Liza, at the end the pumpkin stops. It hits the ground, it has 0 velocity. And that's true, but after there's been a massive change in acceleration. So the acceleration is constant for most of that time, and then there's a huge change in acceleration right as it hits the ground. And so we can't use this equation and assume that the final velocity is 0. It's fine if we want to figure out what the velocity is right as it touches the ground and then use this equation, or use this equation to find the velocity right as it touches the ground. But we can't use this equation and assume that the final velocity is 0. So just a little warning there. If we're going to use the constant acceleration equations, make sure that there's not going to be any massive changes in acceleration. Hopefully that gets you started thinking about kinematics in 2 and 3 dimensions, and we're going to continue to do lots of problems and get lots of practice with this, including doing some things in vector form, but I don't think you're going to need that in the next little bit. So we'll talk about that later.